Hello, AP Physics 2 students. If you are actually one of my students, that means that you are most likely a senior. This is an elective course, and there's currently a global pandemic happening. So if you clicked on this and any of that applies to you, kudos to you for trying to learn despite it all. Let's do this. Let's talk about some refraction. So earlier we talked about reflection, that a light ray can reflect off of a surface and that the angle of incidence is equal to the angle of reflection. Today we're talking about refraction. So that is the change in direction of a light ray that's caused by the light ray changing speed as it goes from one material to another. This may be surprising to you that light can change speed. A lot of people think that the speed of light is the speed of light, but what we know is the speed of light, 3 times 10 to the 8th meters per second squared, is really the speed of light in a vacuum. So the speed of light does change as it moves from a vacuum into a different material, or even just from air to water, things like that. However, it doesn't change drastically, but it does technically change. So an index of refraction, the symbol for that is a lowercase n, and it is the ratio of the speed of light in a vacuum, which we call c, to the speed of light in a material. So if you're working on a problem, it doesn't give you the index of refraction, but you need one, and the light ray is moving through air, we say that the index of refraction for air is 1 for most purposes. You can use that in a crunch. Snell's Law, I know that this has a lot of information on it. Let's just take a look at the images because that's all we really need to figure this out. So we have a flashlight. Someone is shooting light at water. So we have our incident ray here. So some of that light is reflected off of the surface of the water. So we have theta 1 and theta 2 there. According to our law of reflection, those should be equal to each other, and that is still true. However, some of that light is refracted into the water. So here they tell us the index of refraction for air is going to be 1. The index of refraction for water is going to be 1.33. So the light in this first image is going from a lower index of refraction to a higher index of refraction. And the rule here is that if you're going from a lower to a higher index of refraction, the refracted ray bends towards the normal. So you could see that if I extended this incident ray, it would go this way, but our refracted ray is not lined up with that incident ray. It is slightly bent towards our normal line. So that normal line is our line that is perpendicular to that surface. The opposite then is also true. So let's say we have an underwater flashlight and we are shining it at the surface of the water. Some of that incident ray is reflected off of the surface. We still have our law of reflection working perfectly fine. Some of that light goes through that surface and into the air. But in this case, we're going from a higher index of refraction to a lower index of refraction. So if I extended that ray, it would go like this. You can see that our refracted ray has bent away from the normal. So these little rules here are pretty helpful to remember and are kind of the main idea for refraction here, or one of the main ideas. All right, so then if we take a look at Snell's Law, so just a note, usually anything associated with the incident and the reflected rays, we use subscript 1. All variables associated with the refracted ray, we use subscript 2. And don't forget that all of these angles are measured relative to our normal. So Snell's Law is saying that n1 times the sine of theta 1, so your index of refraction of your incident surface, you could say, or material, times the sine of that incident angle has to be equal to n2, the index of refraction of that second material, times the sine of that angle of refraction. Very, very useful equation there. We also have apparent depth. So if you've ever been around a pool or something and you are trying to reach for something at the bottom of the pool, but your head is above the surface, oh my goodness, buddy, hello. You may have noticed that your depth perception is off, that you have to actually reach farther than it seems like you should. And this is an equation to actually solve for that. To be honest, I have almost never used this, but it would be really helpful if that's what you were trying to solve for. So there you go. All right, TIR, total internal reflection. I'm trying to keep this video short since I know this isn't necessarily the most exciting way to spend your time. But again, thank you if you've made it this far. TIR is actually very, very useful and has practical applications. So total internal reflection means that your angle of incidence reaches something called our critical angle, where the angle of refraction is 90 degrees and the refracted ray points along the surface. So TIR actually is when all of our incident light is reflected back into the medium from which it came. So when the angle of incidence exceeds that critical angle, there is no refracted light. So let's go back to our image because I think that will be helpful. Imagine I have my flashlight underwater, just casual things. Flashlight underwater, shooting it at the surface. Well, if I have total internal reflection, that means that my incident angle is greater than my critical angle and no light is being refracted. It is all bouncing off of the surface. So it's pretty interesting visually because you can look at, and I will post some YouTube videos of people with like lasers underwater, and it's pretty cool because nothing is coming through that interface right there. It is all being internally reflected. I worked at a biophysics lab where we used lasers to take pictures of DNA essentially. That's the easiest way to explain it. So I would have to prepare the slides and then use the laser. I'd have to line up the laser, get it into TIR in order to take the picture. Definitely hit myself in the eyes with the laser a few times setting TIR up, but it is very cool. And I will post some images so you can see it, which would be helpful. Here is what I was talking about. So here we have our angle is not greater than our critical angle, so we do have some refracted light. Here our angle is equal, our incident angle is what I mean, is equal to our critical angle, so your reflected ray is just along the surface. And then if you surpass that critical angle, you have TIR and everything, all of the light is reflected internally. There's no refraction. The next part of this part of the unit is about lenses. So we talked about mirrors and reflection, and we practiced sketching where our images will be. And now we're going to talk about lenses. And for lenses, we're talking about refraction. So lenses are made from transparent materials that refract light. Obviously, we use lenses in cameras and glasses, things like that. And they refract light in such a way that an image of the source of the light is formed. So focal point and focal length is the same idea as we used for mirrors. And instead of concave and convex, we have converging lenses and diverging lenses. Converging lenses cause incident parallel rays to converge at a focal point, and diverging lenses cause incident parallel rays to diverge after exiting the lens, which you will see in a second. So lenses are different from mirrors because light can pass through them from left to right or from right to left. So you could have your object on either side of the lens. And to construct ray diagrams, which we did with mirrors, we need to begin by locating a focal point on both sides of the lens. I took this straight from your textbook because it explains exactly what's going on. But if we want to sketch our image for a converging lens, so let's say our object, we have our focal points, we're going to put it on both sides. Notice how a converging lens goes out like that. It is the opposite of, I'll just show you our diverging lens, which goes in. So our object is to the left of our focal point here. Our first ray initially travels parallel to the principal axis and then is refracted so that it goes through the focal points on the other side. Our second ray that we can draw goes through that initial focal point and then is refracted parallel, so just the opposite of the first one. And then we have our third option, which goes through the center of the lens. So remember, you need to sketch at least two of these and have them intersect, and where their refracted rays intersect is where your image will be. If you want to sketch all three, be my guest. You may not need to, you may need to. Diverging lenses, a little bit different. So we have our parallel ray, and it refracts such that if you extend that refracted ray, it'll go through that focal point that's on the same side of the object. For the second ray you can draw, it goes initially as if you extended it, it would go through that focal point on the opposite side and refracts parallel. And the third one is the same. It just goes through the center. So definitely use these two slides as a resource when you are practicing problems. And then we also have our thin lens equation. So 1 over d, the distance of the object, plus 1 over the distance of the image equals 1 over the focal length. And then you have a magnification equation, pretty similar to mirrors. So this last slide is summarizing our rules and sign conventions for lenses. You will find a lot of what is true for a concave mirror will be true for a converging lens, and same for diverging and convex. A lot of that is the same. Let me know if you have any questions. Hang in there, and bye.